Welcome back everyone. So in this lecture we are going to learn about extrinsic semiconductors. So extrinsic semiconductors are also called as impure semiconductors. So extrinsic semiconductors are also called as impure semiconductors. So for intrinsic semiconductors, if you add impurities, then it becomes extrinsic semiconductors. So intrinsic semiconductors is added with impurities, so it becomes extrinsic semiconductor. So this process of adding impurities is called as doping. So the process of adding impurities to the pure intrinsic semiconductor is called as doping. So in extrinsic semiconductors, so as doping increases, then conductivity will increase. So basically there are two types of extrinsic semiconductors. One is N-type semiconductor and the other is P-type semiconductor. So this classification is based on the types of impurities added to the intrinsic semiconductor. So if fifth group elements like phosphorus, arsenic, antimony and bismuth. So if fifth group elements are added to the pure intrinsic semiconductor, then that type of semiconductor is called as N-type semiconductor. So similarly, if third group elements, for example boron, aluminium, gallium and indium, are added to the pure intrinsic semiconductor, then such type of extrinsic semiconductor is called as P-type semiconductor. So this is the classification of extrinsic. Basic crystal structure of N-type semiconductor, and this is the energy band diagram of N-type semiconductor. So here the fifth group element is added as the impurity in the case of N-type semiconductor. So the fifth group element has 5 valence shell electrons. So 4 of the 5 valence shell electrons are involved in covalent bonding with the intrinsic semiconductors atoms, and this electron, the remaining one electron will be bounded to this impurity atom. So this is not free now, so it is bounded to the impurity atom. So this is how the crystal structure will be there in the case of N-type semiconductor. So 4 electrons will be involved in bonding with the 4 adjacent intrinsic semiconductor atoms, and 1 electron will be bounded to this impurity atom. So at 0 degrees Kelvin, that is when we don't apply any external force or external temperature, then all extrinsic, this is very important, so all extrinsic and intrinsic, so all extrinsic and intrinsic semiconductors, they act as insulators. So even though there is 1 electron which is not involved in bonding, but it is still bonded to the nucleus of this impurity atom. So at 0 degrees Kelvin, so all extrinsic and intrinsic semiconductors will act as insulators. So when an external force is applied on this N-type semiconductor, then what will happen? So this fifth electron which is bounded to this to the nucleus of the impurity atom will become now free. So if you represent it with A, so this as A dash, so this can be seen in the energy band diagram here. So this is A and this is A dash. Similarly, when you apply some external force, the covalent bonds will also break down, then this and then electron hole pair generation, as we have discussed in the previous class, electron hole pair generation will be occurred, and then one hole and one free electron will be formed. So if we take this as represent this as B and this as B dash, so that can be represented here as B and B dash. So the important thing here is this process where you are having electron hole pair transition is called, electron hole pair generation is called as band to band transition. So band to band transition. Why it is called band to band transition is the electron, by acquiring energy, is jumping from valence band to conduction band. So that type of electron hole pair generation or free electron generation is called as band to band transition, and this free electron generation is called as impurity ionization. Impurity ionization. So why it is called as impurity ionization is this electron is due to the impurity atom. So this electron is due to the impurity atom, and this impurity atom, by donating this electron, it is now becoming a positive ion. So this impurity atom, by donating this atom, by donating the electrons, when electrons are being donated by any atom, they will become ions. So if they donate the electrons, they become positive ions. So that process where impurity is getting ionized is called as impurity ionization. So free electron generation in the case of N-type semiconductor is due to two processes. One is general band to band transition. This band to band transition is common in both intrinsic and extrinsic semiconductor, and impurity ionization. So impurity ionization is only occurs in the case of extrinsic semiconductors. So these two processes are mainly causing the current conduction in the case of N-type semiconductor. So these two processes can be observed in energy band diagram also. So this process where the electron hole pair generation occurs, where electron acquires some energy and jumps from valence band to conduction band, that is from B to B dash, is shown here, is band to band transition. And these fifth group elements which are lightly bounded to the nucleus of impurity atom is there in the next energy level. So this energy level is called as donor energy level. Donor energy level, because the impurity is called as donor impurity, because by donating the electron, the impurity atom is supporting the current conduction in the case of N-type semiconductor. Therefore, this process is called as, or this impurity is called as donor impurity. Generally, it is represented by Nd. That is, the total number of donor impurities is represented in N-type semiconductor as Nd. So this is called as donor energy level, and the amount of energy required is 0.01 electron volt for germanium and 0.05 electron volt for silicon. That is, very small amount of energy is required to excite this fifth electron, which is bounded to the nucleus of the impurity atom. So it is shown in different energy level, which is about to become free. So it is shown near to the conduction band, because all the electrons in the conduction band are of type free. Okay, so this is the band diagram and crystal structure and the phenomenon of the current conduction in the case of N-type semiconductor. So if you observe here, the total number of free electrons are more when compared to the total number of holes. So this is the reason why, so electrons Electrons are called as majority carriers, and holes are called as minority carriers. So electrons are called majority carriers and holes are called minority carriers in the case of N-type semiconductor. Okay. So next we will discuss about P-type semiconductor. So next we will discuss about P-type semiconductor. So in P-type semiconductor, we are going to add third group elements as the impurities. So third group elements consist of 3 valence electrons. So this represents the crystal structure of P-type semiconductor. So 3 valence electrons are bounded to the 3 adjacent neighboring atoms which are intrinsic, and 1 electron. So this is not having any electron, and since it is involved in bonding, so non-existence of this electron is called as hole. So hole will be there in the 4th bond. So when an external force is applied, as we have discussed for N-type semiconductor, similarly, so if an external force is applied, then electrons will acquire energy and comes out of bonding by the process of electron hole pair generation, so EHP generation. Therefore these electrons are coming out of bond and will have the free electrons. So if you observe here the total number, so due to this process, if you take consider only 2 electron hole pair generation has been occurred, then the total number of free electrons are 2 in number, but the total number of holes in the crystal structure are 4 in number. So this is 1, 2, 3 and 4. So totally 4 number of holes and 2 number of free electrons. So this is the reason why electrons are called as minority carriers. So electrons are called as minority carriers and holes are called as majority carriers in the case of P-type semiconductor. So in P-type semiconductor, they are called as holes are called as majority and electrons are called as minority carriers. So the electron, so this empty covalent bond will always tries to attract the electrons. So by accepting the electron, P-type semiconductor will support current conduction. So the impurity in this case, that is the third group element, which is the impurity in this case, is called as acceptor impurity. So by accepting an electron, because it consists of one hole which always attracts the electrons, so it is called as acceptor impurity, generally represented by Na. The amount of impurity atoms in P-type semiconductor is represented by Na. So acceptor impurity. So both process which I have discussed for N-type semiconductor will always exist for P-type semiconductor as well, that is both band-to-band transition and impurity ionization. So here impurity is getting ionized, but it is getting negatively ionized. So that is the main difference between N-type semiconductor and P-type semiconductor. So impurity atom is getting negatively ionized in the case of P-type semiconductor, and it is getting positively ionized in the case, because it is donating electron, so it is getting positively ionized in the case of N-type semiconductor, but it is getting negatively ionized in the case of P-type semiconductor. So these are the major differences between N-type semiconductor and P-type semiconductor. So majority and minority carriers are reversed, and the impurity is called as acceptor impurity, and the impurity atom is getting negatively ionized in the case of P-type semiconductor. Rest, the remaining all concepts are similar for both N-type and P-type semiconductors. So next we will discuss two very important points. First one is all intrinsic and extrinsic semiconductors are electrically neutral. So they are electrically neutral. So in the case of intrinsic semiconductor, this statement is valid directly because the number of free electrons is equal to number of holes. So negatively charged particles is equal to positively charged particles. Therefore it is electrically neutral. But in the case of extrinsic semiconductor, I have told you that electrons are majority carriers and which are more in number, and holes are minority carriers which are less in number, but still how extrinsic semiconductor is electrically neutral. So the point here is in the case of N-type semiconductor, the total number of electrons, the total number of free electrons is equal to number of holes. So number of free electrons is equal to number of holes plus number of positive ions. So it is also equal to the total number of positive ions. So number of free electrons, as we have discussed in the case of N-type semiconductor, so number of free electrons is equal to number of, how these free electrons are formed by two processes. One is due to band-to-band transition. In band-to-band transition, so total number of free electrons is equal to total number of holes. That is one process, and the other process where free electrons are formed is due to impurity ionization. So in the process of impurity ionization, the number of free electrons which are formed is due to the donation of electrons by the impurity atoms. That is, the total number of free electrons formed due to impurity ionization is equal to the total number of positive ions which is formed by the impurity atoms. So thereby the total charge of a negative charge, the total negative charge is equal to the total positive charge, and hence still the extrinsic semiconductor is also electrically neutral. Similarly, in the case of P-type semiconductor, so in the case of P-type semiconductor, total number of holes is equal to total number of free electrons plus number of negative ions. As I have told you, the impurity atom is getting negatively ionized, so total number of holes is equal to number of free electrons plus number of negative ions. So you have to remember that both intrinsic and extrinsic semiconductors are electrically neutral. And second important point is to comment on the type of semiconductor. So if a semiconductor is given for you and asked to find whether the given semiconductor is of P-type or N-type, always compare their carrier concentration. So we have to compare their carrier concentration instead of currents. So instead of currents, you have to compare the carrier concentration. So if the total number of free electrons is equal to the total number of holes, then that type of semiconductor is called as intrinsic semiconductor. So if the total number of free electrons is not equal to the total number of holes, then that type of semiconductor is called as extrinsic semiconductor. And again, in extrinsic semiconductor, if the total number of electrons are greater than the total number of holes, then that type of extrinsic semiconductor is called as N-type semiconductor. Similarly, the total number of electrons is less than the total number of poles, then that type of semiconductor is called as P-type semiconductor. Okay, so this is how we can classify the type of semiconductor based on the carrier concentration. Okay, so by this concept, the entire concepts of extrinsic semiconductors are completed. So in the next class, we will discuss the remaining concepts of small important concepts regarding the semiconductor basics. Thank you.